So, can we use a linear boundary here? I mean, you might be thinking, okay, this is really great. Like, we've got this great classifier that's flexible. We can violate the margin. We can violate the hyperplane. Like, we're done. But it turns out, actually, we've got data that may have nonlinear boundaries or may need a nonlinear boundary. So what do we do? I mean, any kind of linear classifier will perform poorly here. You can't just draw a line through this data and think you're classifying things correctly. So we can make the procedure more flexible by enlarging the feature space and using functions of the predictors like polynomials or splines and higher order, and so using basis expansions in other words. So what does it mean? What do I mean in mathematical terms? Like, instead of using a support vector classifier with p features, we can instead fit a support vector classifier with 2p features. So that's what I was trying to show you up here. You know, you've got this one, this one, this one, so 2p features. And so we'll maximize our margin subject to all these beta coefficients and subject to this yi and the function of those coefficients greater than or equal to some margin, and this is our slack variable, and again the slack variable is bounded by, the sum is bounded by our constant, and we've got a bound on those coefficients. And so why does this actually lead to a nonlinear decision boundary? In the enlarged feature space, the decision boundary that results from this equation is actually linear. But in the original feature space, the decision boundary is a quadratic polynomial, and so the solutions are nonlinear. So what does that mean? Like, what does this look like? Because I wanted to find a bunch of pictures of what we're doing. Like, it helps me to just see what's happening here. So this is the idea. Like here, this is, you know, low dimensions. How do you separate this data? You can't just draw a line. But if we actually use a nonlinear boundary, we can actually come up with a linear hyperplane in a high dimensional space. So we're separating data points down here and up here. And so that's the idea of support vector machines. We can actually find linear boundaries in the enlarged space, and that will help us to get better training separation. And even though it's linear in the enlarged space, it's still nonlinear in the original space. Does anyone have any questions about that? Looks cool? Yeah.
Outside of like just looking at bivariate plots, is there any numerical measures to determine when it might be necessary to go into these higher order, and outside of just kind of like on your fat, so just looking at the bivariate plot? Any like diagnostics other than, I don't know, going with reduced versus larger models?
Okay, thank you.
I think when you have a ton of variables, I'm trying to explore. I mean, maybe then it's not even necessary to ever go so many variables. I was just curious.
No, that's a good question, because every time, well, when it helps me to see what's happening, and when in all the pictures that I have, you'll see why it might be better to have a nonlinear boundary. But as far as knowing when to have one, yeah, I'm not sure. But that's a good question. Good to look into. So I guess maybe if you're not doing a very good job separating it with linear boundaries, then maybe try a nonlinear one. That's probably what I'd do.
Do you ever include greater than the second degree?
Oh yeah, definitely. Like
a reason why you do that compared to just keep trying different things?
I think so. I think it's like just keep trying different things. Yeah, I think so. And other people feel free to comment. So. All right, so it turns out that the solution to the support vector classifier problem involves only inner products of the observations as opposed to using the observations themselves. So, you know, we've got the definition of an inner product up here. So we can actually rewrite our linear support vector classifier like this using that inner product. And it can be rewritten like this because it turns out that the alpha i's here are non-zero only for the support vectors in the solution. So support vectors are actually those observations that lie on the margin or that occur on the wrong side of the hyperplane. And so our solution, like our classifier, really only needs to be a function of those support vectors, which is a nice thing about this classifier because we can actually, it reduces the space that we need to find a solution for. And so it makes it more computationally feasible. So that's why we have this S here. This is actually the collection of support vectors, which, like I said, lie either on the inside of that margin or on the wrong side of the hyperplane. Even though we have this reduced space here, we're still dealing with a lot of inner products that we need to find. So it turns out that we can actually use kernels, which are generalizations of that inner product and are computationally feasible. And so I'll just go over a little bit of what that means. A kernel is a function that quantifies the similarity of two observations. So using a kernel with d equal to 1, d dimensions equal to 1, we go back to our usual inner product that we all know well. If we have a d greater than 1, then the support vector classifier uses a much more flexible decision boundary. And so when you combine the support vector classifier that we talked about before with the flexible soft margin with this nonlinear kernel, we get a support vector machine. So that's how we go from the support vector classifier in the linear space to a support vector machine in a nonlinear boundary, in a nonlinear space. And so here are three popular choices. We've got the dth degree polynomial, the radial basis, and the neural network. And the dth degree polynomial is basically fitting a support vector classifier in a higher dimensional space with polynomials of degree d, rather than fitting these polynomials in the original feature space. And the radial kernel, basically, it's a local fitting kernel. So if you're given a test observation, so if you can see like the definition here, if you're given a test observation, if a test observation is far from the training observation, so this is actually like, maybe we'll call this the test or training, it doesn't matter, then the norm between the two observations will be large, so the kernel itself will be small since we have this exponent of negative of this distance. So basically that's telling us that observations that are far from the training observations that are far from the test observations will play no role in predicting the class label for that test observation, whereas training observations that are close plays a bigger role. So it just helps us to determine it's a local fitting. It has local behavior in that only nearby training observations have an effect on the class label. So that is the idea there. And the neural network kernel is also known as the sigmoid kernel, is equivalent to a two-layer perceptron neural network, which Neil talked about. And so it just uses two different layers, and you can read more about exactly what the hyperbolic tangent means and all of that. But these are the three popular choices. So if you were to read literature on kernels and things, you'll probably run into one of these three, and probably the first two. I haven't really seen a whole lot of neural network stuff. So what's the advantage of using a kernel rather than just enlarging the feature space using functions of the original features? The one advantage is computational, because like I said here, we only need to find n choose 2 distinct pairs of our support vectors instead of n choose 2 of all the observations that we have in our data set. So it cuts down on that computational work, and it can be done without actually working in the enlarged feature space, which is nice because some kernels, like the radial kernel, has a feature space that's infinite dimensional, so we can never do computations there.